Okay, so strength of materials. Let's go over the syllabus first. So this is the book. Does it look familiar to somebody?
Oh, I think I have it.
Okay. You can have mine.
Yeah. You gave them on the end of last semester,
I have.
and I think I forgot to do that.
Okay, I want to check that. All right. Okay, so that's the book, 9th edition, Mechanics of Materials. If you're using the 8th edition, that's fine too, because the 8th edition is essentially differs from the 9th edition only in the sense that Hitler wanted more royalties. So that's pretty much what it is. So we're going to try to cover all 14 chapters. We'll see how far we get. You know, I've never worked through this book, so I don't know whether we're going to make that or not. But the focus will be primarily on the first 12 chapters. So the buckling of columns and the energy methods will be, if you notice on the schedule on the 3rd page, they're one lecture each at the end. So they may or may not get covered. Okay. All right, so there's 2 midterm exams. The 8th of October and the 12th of November. Midterm exams are typically 2-hour exams. And we'll figure out, based on sort of a consensus of the class, whether we do that as 2 1-hour exams in class, or we do it as a 2-hour exam in or out of class, or however we handle it, but it will be a 2-hour exam. And there are 2 class periods devoted to it. So if we do it as a 2 hours out of class, or extend the class or something, then one of those 2 will become a problem session. We can work through some extra problems. Okay. Each of the exams is 100 points. Final exam is 200 points, and the homework is 100 points. So a total of 500 points in the class. The homework's on mastering engineering, just like mastering physics, except it's engineering. Has anybody tried to get on yet? They're mastering? No. Okay. So I suggest you get on that fairly quickly. You'll need to recognize this book because you have to specify this book when you log in. So even if you're using the previous edition of the book, you want to specify this one when you log in, because this is the one on which the course is based. Okay, so make sure you specify that. And then the course ID is given there under grading, under the homework. It's ENP302, fall 2014. So you'll need that when you get in. Then your student ID is just your 8-digit student ID. So there are 8 homeworks. They're each weighted equally, so 12.5% or 12.5 points per homework, independent of how many questions are in the actual homework assignment. Okay. Homework that is late is penalized 1% per hour that it is late. Typically, homework is due the class period, 2 class periods after we finish covering the material in class. So you'll notice we finished covering the material from chapter 2 on the 5th, on that Friday. The homework for that one is due on the 10th, the Wednesday after. So that gives you 1 class period in between when we finish the material and when the homework's due to ask questions if you have questions. Okay. But the penalty for being late maxes out at 50%. So there's still 50% credit for incomplete homeworks all the way out to the end of the semester. So if you don't get through it, you can still get some points back by completing it later. Okay.
Do you do the same thing that Davis does, where he puts more points than?
No. So the full credit, however, well, yes, actually I do, but not in the way that Davis does it. So if you read the last sentence, see, it's amazing how much of the stuff is actually in the syllabus, if you read the syllabus. Anyway, so you will get full credit for achieving 60% of the assigned points for each homework, whatever that number of assigned points is. So unlike Davis, where he puts, you have to get 50 points, whatever, he specifies a point value, I just specify 60%. The idea there is the purpose of homework is for you to learn the material. If you learn the material by doing 2/3 of the homework, then you shouldn't have to be forced to do the last third. There are essentially 3 problems for every class. If you look on that sheet, you'll see that there are 3 problems assigned for each class that we cover. So if you only need 2 of them to really practice and master the material, then that's sufficient, okay? So the other 40% is there for you to practice. And if you go through it and you do the first 2 problems, you meet the minimum requirement, you say, you know, I just don't feel like I really understand this stuff well enough, then you keep working on the other ones. Okay, the purpose of homework is not to assess your mastery of the material, it is to develop your mastery of the material. Okay? So that's why there's a 60% threshold. So you can pick which 60% you do. There's no particular set of problems, yeah.
It's been a little while since I used mastery physics. Will it tell us when we've hit our perfect score at the 60% mark?
No, you have to just keep track of it yourself.
Okay.
So you know how many points are assigned
Right,
to each
okay.
homework, and then you can just keep track of how many points you have amassed.
Okay.
Okay. So what the bottom line there is, everybody should get 100% on homework. There's no penalty for wrong answers. The homework is there for you to learn. Because the reality is, no matter what I sit up here and blah, 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 I can talk all I want, you will learn when you go through the repetition of doing the homework, solving the problems. You won't learn from watching me. I mean, hopefully you learn something, otherwise, you know, I become superfluous. But the point is, you know, the main learning occurs when you actually do the homework. Okay. And again, there's no penalty for wrong answers, so keep trying until you get it right. No quizzes. There are no quizzes, but there may be a quiz if I feel like people are not really, you know, because I can see what everybody's doing in their homework. If nobody's doing the homework until the night before the homework is due, then maybe I'll pop a quiz in there to say, hey, perhaps it would be a good idea to try to master homework along the way instead of waiting until the end. Does that seem fair? Okay. Then there are also video examples on mastering engineering. Essentially, it's somebody else solving problems. It's kind of like pen casts, you know, the Gagner's pen casts, but it's somebody else doing it. So I've included all of those as practice problems. I mean, there are actually questions involved as well. In you know, they show you the solution and they sort of ask you, so what's the next step, that kind of thing. Those are purely practice. They have no impact on your grade. They are there for you to be able to see somebody else solving problems. If my particular approach is not resonating with you, maybe somebody else's will. Okay, so it's there just to serve as another resource. Okay, so that's a total of 500 points, and you can see there the grading scale and the course structure. Any questions? No questions. All right, then let's jump in. So strength of materials, or sometimes called mechanics of materials. So the question is, what is strength of materials? Everybody remembers rigid bodies from statics, right? Rigid bodies. Everything was a rigid body. Well, maybe a particle, but most of it was rigid bodies, okay? What was a rigid body? Rigid body was something that had mass, or maybe not, but it had a finite size. The key with a rigid body is it's rigid, it doesn't deform. Strength of materials now allows for those bodies to deform. Okay, they can experience stress and strain. Remember stress? You guys know what stress and strain are? Now we'll talk about that again. So they can experience stress and strain. So now it's essentially statics plus deformation. So instead of just being some steel member between pin A and pin B, it's now a steel member that might bend or buckle. Right? There might be some change in its size. So since it's basically statics on steroids, we're going to go back and look at the key elements of statics. What was the main key element from statics was everything was in equilibrium. Right? That was the cornerstone of statics. Everything's in equilibrium. What does equilibrium mean?
Balance.
Balance?
No translational animation.
Actually, doesn't mean there's no movement, though generally there wasn't. It means that there's no acceleration. The distinction for equilibrium is there's no acceleration. right? This table is in static equilibrium, right? But it is moving. It's hurtling through space at 20,000 miles per hour. But relative to the Earth, as our reference system, it's not moving. So velocity, you can have velocity and still be in equilibrium. You just can't have acceleration, right? So it has to be in a state of no acceleration relative to its reference frame. Okay. So equilibrium means, in order for there to be no acceleration, that means the sum of the forces in whatever dimension is equal to 0, and the sum of the moments about whatever dimension is equal to 0. Right? That was our key, that was the key cornerstone of every statics problem. Right? Okay. And we can rewrite that as just the sum of the vectors, or we can write it as the sum of the forces in the x direction is equal to the sum of the forces in the y direction is equal to the sum of the forces in the z direction is equal to 0. This is vector notation on the left, this is scalar notation on the right. Right? So that's why I drew the vector over the ones on the left, but not the ones on the right. And so by breaking it down into each of its component directions, it becomes a scalar problem. Although, inevitably in class, I'll forget to draw the vectors half the time. Okay, so just, if there's ever a question, wait, is that a vector or scalar? Let me know, okay? And similarly, the sum of the moments about the x is equal to the sum of the moments about the y is equal to the sum of the moments about the z, which is equal to 0. Okay? So in the most general three-dimensional sense, there are 6 equations that we can derive for a body in equilibrium. And in a two-dimensional sense, this one goes away, this one goes away, and that one goes away. Right? Because if my board is my 2 dimensions, then I can have forces in the x, forces in the y, but no forces in the z because it's a coplanar. It's a coplanar force system. Everything's in one plane. But I can have moments in the z. Right-hand rule. If I have any kind of a force acting out here, the rotation's always going to be about the z in a two-dimensional system. So the 3 pieces that exist in a two-dimensional system are the x, the y, and the z moments. Everybody remembers that, right? So, okay. So, and then in statics, we talked about a couple different kinds of forces. Right? So this is all just sort of review of the stuff that we've done. So there's kinds of forces. The first was a concentrated force. Concentrated force is one that acts at a point. Now in reality, any real force, there's no such thing as a point. Right? Any real force is distributed over some area. Even if I prick myself with a pin, right, the head of the point of that pin has some defined area, so the force is distributed over the head of that pin. But that area is so small compared to the system, my body, that it's considered to be a concentrated or point force. Right? So we draw those with arrows. Right? You have a beam, supported on both ends, and we have a force acting in the middle. That's a concentrated force. Okay, everybody remembers that? What other kind of force do we have? It's not concentrated. What is it? Distributed force. Right? Distributed force. In 2 dimensions, we typically drew distributed force something like this. Remember those? Okay. So it's not, in this case, a non-uniform distributed force. It could be a uniform. It was a rectangle instead of a triangle. And in distributed forces, we talked about we have some force per unit length. Right? So if it was just if it was a triangle, or I'm sorry, if it was a uniform distributed force on my beam, I might have something up here that says 3 kilonewtons per meter. right? There's a force per unit length. Or it could be a force per unit area, though I doubt you probably covered much of that in statics. Probably not a lot of two-dimensional force distributions. There might be some. Anyway. And then what you do to handle a distributed force is we say, well, then we take we generate a resultant force that is the integral of this. That's going to be F. Force per unit length is lowercase f. So we took the integral of F dl along the length of the bar. That makes sense? And we're essentially integrating the area under this force distribution. In this case, F is a constant. It can come out and we just get F times L, 3 kilonewtons per meter times 2 meter length. In this case, F depends on L, so we actually have to do the integral, but it's 1/2 base times height, so we can do integration of the triangle very nicely. Right? But if it was something else, some kind of curve or something, we had to actually do the integration. You guys did remember doing it? Okay. So we get the resultant force, and then where does that act? Where does the resultant force act? If we take this distributed force and turn it into a concentrated force, a resultant force, where do we apply that resultant force?
If it's the straight line in the middle, it's the triangle is the 2 thirds.
Okay, but how would you define that in words instead of picking those particular locations? The particular word I'm looking for begins with a C. Centroid. The force is applied to the centroid. Right, so it goes through the centroid of the triangle. And the centroid of the triangle is indeed, as Kayla said, 1/3 of the way in from the high end of the triangle. So it would be applied some kind of a resultant force here. Right? Yeah, I remember that now. And the word centroid actually makes sense now that someone else has said it. Right? Okay. These two are both surface forces. Whether they're concentrated or distributed forces, they are forces that act on the surface because something's touching the surface. Right? In this case, it might be cars on a bridge. Right? It's some kind of external applied, but it's applied to the surface of the bridge. There's a third kind of force, body forces, that are applied uniformly to every element of mass in the body. Those would be things like gravity, or some kind of electromagnetic attraction. All right, next, we also have, okay, so in this picture, have I drawn all the forces on this beam? What am I missing? Reaction forces, right? We gotta draw the forces up the end. So we have another category of force, reaction forces. And in this case, I think what you're talking about is what we would call support reactions. Right? The reactions from the supports, the ends of the beam. So in 2 dimensions, which is where most of your statics work, there's several different kinds of reaction forces. Right? So there could be a cable or a rope. A cable or a rope attached to the end of the beam. So I've got my beam here, and I have a cable attached to the end. A cable or a rope generates how many variables are there with a cable or a rope attached? How many unknowns do I have? How many forces does that cable or rope generate?
One.
Okay, I'll give you credit because you had the one up first. Yes, it generates one. There's one force. And there's really only one unknown. Because the direction of the force is already defined by the cable itself. Cable can only support a force along its length. Right? And what's more, we know that it's tensile. Cables can't support compressive forces. They can't push, they can only pull. Right? So that's the simplest support reaction, is a cable. One force, one unknown, we know its direction, we know its tensile, we just don't know its magnitude. Next would be a roller. These kinds of things. All right. Roller. What kind of force does a roller exert? How many forces? How many forces from a roller? One. Do we know its direction? Right, it's perpendicular to the surface on which the roller is rolling. So we are left, therefore, with just the one unknown. And we know that the force has to be up. It doesn't have, it's not attractive. So again, it's just up. I'm not going to, tensile or compressive doesn't really mean as much in this configuration. Okay, how about a smooth support? Let's do it this way. Say we have some kind of a beam sitting out here. All right, see what I mean by smooth support? So it's a smooth surface. How many forces? Say it out loud.
Just the one.
You have one. Did you vote for two? Did I hear somebody else? Did you?
I voted for two.
All right. We got to vote for one. We got to vote for two. Anybody else want to side with one of them?
Vote for two.
I vote for two. All right. Everybody voting for two, raise your hand, and it only counts if your hand's above your head. All right. Everybody voting for one.
Well, I guess I'll say one.
All right, good choice, because there's still only one force.
I think you guys are thinking the components.
Well, friction, I didn't know if that would count.
That's why it's a smooth surface.
Oh, is that
A
what?
smooth surface doesn't have friction.
Ah,
Okay. So one force, do we know its orientation? Do we know the orientation of that force? It's perpendicular to the surface. Therefore, there's still only the one unknown. Right? We know its orientation is perpendicular to the surface. Not perpendicular to the bar, perpendicular to the surface. All right, how about a rough surface? How many forces? Two. Two. Any other thoughts? We're going to go with two because that's how we roll. All right. What's that?
Can you, they were saying friction before, but can you one friction and the reaction force?
Yeah. So there are kind of two forces. I'll put it in quotes because there's still only one unknown, assuming you know the assuming you know mu. Because mu depends on the normal force. So those two are interrelated. There's an interaction between the two, which is mu. So there's really only one unknown. Because their orientations are fixed as normal and parallel to the surface. Okay. So far, everything's just one unknown. Then we have a pin. Ooh, not very well drawn pin. pin. How many forces? Now there are two forces.
Does it depend on if the pin is attached to one of the supports? If the pin was attached to one of the supports, would it only be one force?
I'm not sure I understand what you mean.
If the
So in other words, if
pin,
this was the ground?
if the pin was extruded from, say it's like a molded in pin, it's not.
Oh, rigidly attached to one of the, no, because it can still, if it's rigid to this one, it's not rigid to that one.
Right, so is that
So it
one
can still
force?
exert two forces on this one, there can
Okay.
still be two reaction forces. And it doesn't matter whether this is attached to the ground or not.
Right, I know.
Okay, as long as it's free to move about one of the two, then you have rotational freedom. So it doesn't have to be rotational on both of them. And generally it won't be, right? Generally, one of them will probably be fixed. Okay, so two forces, how many unknowns? Two, because there's no moment. Right. Well, how do I get a moment? Sink it in concrete. Right, just embed the bar in the supporting surface. Now, not only can it support vertical and horizontal forces, but it can also support a moment as well. So now we have two forces, one moment, and three unknowns. So remember all those now, hopefully. Okay. Sort of a screaming fast review of the basics of statics. What are we doing here? 29, we got plenty of time. Okay. Okay, so those are all the support reactions. Then there's one additional kind of force. And that is the internal reactions. Those are all external. The supports are all external. So now we have internal reactions as well. So if I have, I take a cross section of a beam, right, or a post or something. So that's what I'm going to do here. I've got a cross section. Now let's go to some other colors. So on this top cross section that I've cut out of the beam, there could be a force and a moment acting on this internal surface, right? But that force, I'm going to break into two components. I'm going to say, well, here's a normal force, a component of force acting normal to that surface. And then here is some kind of shear force, V. Right, you guys remember, was V what you used, your book used for shear forces last year? You remember? Yeah, it's all fuzzy. That's a full 12 months ago. Okay, so V is a shear force in the context of our class. Okay. But that shear force, even that shear force, and so there's a component perpendicular to and a component parallel to the surface. But that shear force, the one in the plane, also has some orientation theta. So in terms of the internal reactions, we now have, we've already given ourselves three. One is a normal force. Right, so if this is a beam that has some external forces applied to it, and I cut it off, if it's in equilibrium, then there has to be an internal force here to balance the externally applied forces. You guys remember that process? Right? So if there's an externally applied normal force, then there has to be an internal reaction normal force. Perpendicular to the surface. Then there's a shear force parallel to the surface. And there is a shear angle defined relative to some reference direction. This one is N, this is V, and this is theta. Okay? Then, there are also moments. There is a, let's see, let's do the moments in red. There's a moment there, and maybe a moment there. One perpendicular to the surface, and one parallel with the surface. See that? So one perpendicular to the surface is a moment causing a rotation about that axis. And then one parallel to the surface is the one causing rotation about that axis. Does everybody understand the picture? Okay. What's this top one? What kind of a moment is that? One that's causing a rotation about
Y-axis.
about the normal direction, or about the, it's a rotation about the normal direction. Do you know what kind of a rotation is this? What kind of,
Like opposite rotation.
I'm looking for a particular word. Try to give you a hint. We're going to label that one T.
Twisting.
Close. What?
Torque rotation?
Oh, you're even closer.
Torsion?
Torsion. There's a torsion moment, T. Torsion moment is defined as a moment about an axis perpendicular to the surface. Then there is a, what's the other one called? That's the torsion moment. What's this one going to be? How else can we deform something by bending moment? Very good. Do you guys remember the words torsion and bending from last year? Right? Okay. So a torsion and a bending moment. Parallel to the surface. And then, similarly, there would be a bending angle. Which would be the angle relative to whatever that frame of reference is. In this case, I've chosen the x direction. And you do know the three-dimensionality, x, y, and z, everything has to be right-hand rule, right? So, in this configuration, this is x, this is y, and this is z, because x cross y equals z. Okay? So, is that all? Strike a chord of familiarity? Yes.
Can you explain that really quick? Because why couldn't you just rotate it?
So, by definition, x, y, and z, I, j, and k, the sequence in which we do things. In order for the right-hand rule to work, x has to be in the direction you point your fingers, y the direction you bend your fingers, z the direction of your thumb. That's to make the right-hand rule work.
Okay. But why couldn't X be pointing out here and Y could be pointing out here and Z
It could
be
be.
pointing towards
It
this?
could be. All I do is I take this configuration and rotate it in a different position, that's fine. It's the
Okay.
relative position. I could not switch x and y.
Right. But it doesn't matter that Z is pointing up as opposed to pointing out at this.
Right, well, the z has to be orthogonal to the plane, to the xy plane.
Right.
But if x and y are, in this case, right, proton x, y, and z would have to be out of the board.
Right.
But it would have to be out of the board, it couldn't be into the board. Because x is here, y is there, so z has to be out of the board.
Right.
in order for our right interval to work.
But that's not specific to the picture, it could be, it's just a way to label things.
Right, once I choose one, I fix the others.
Right.
Okay. And then if we have a two-dimensional system instead of a three-dimensional system, so that now we're just going to take this thing and look at it two-dimensionally, so we don't allow for a third dimension into the board. Now I can still have a normal force, I can still have a shear force, and I can still have a moment, but the only moment that's left is the z, right? We have the x and y forces, and the moment about z. So in this case, the x and y are n and v. There is no theta. So in 2D, theta equals 0, right? Because v is automatically perpendicular to n and there is no angle. And the only moment that exists is the one about z, the bending moment. There is no torsion moment, and therefore no phi. That make sense? So in 2D, we have just the 3 variables, 3 unknowns. In 3D, we have 6. Which is good because I erased the other stuff. Oh well. The stuff I had up here before. We have six equations in 3 dimensions. We have 3 equations in 2 dimensions. We have 6 unknowns in 3 dimensions. We have 3 unknowns in 2 dimensions. So it all works nicely. Everything can be simple. Okay? All right. Any questions about that? Everybody remembers most of that? Okay, so first homework assignment is to start messing with those. Let's do at least one example problem from your book. Okay. And the way you approach problems in strength material is largely the same way you approach them in statics. It's just how we characterize the results that are slightly different. Okay. So we're going to do 1-5. So anybody has the, well, 1-5 in the new book. I don't know if it's 1-5 in the old book, but it is what it is. Okay, we have a beam on a roller with a central pin. To a fixed support on the other side. And we have distributed load with a peak of 1.5 kips per foot. Anybody know what kip is? What's a kip?
It's an English unit.
It's an English unit. Yeah, okay. Well, we've narrowed that down. Kip.
3,000 pounds.
No. Take your 3 off.
1,000 pounds.
1,000 pounds. It's a kilopound. Right? Kilo, pound, kip. Okay. And then we have a load over here of 3 kips. And we have a point E and a point D, which are located nobody make fun of the scale on my picture. Okay, accordingly. And then just for reference, this is going to be point A, center here is point B, and the pin out here, or the support out there is point C. Okay. And we are to find the resultant internal loadings at points D and E. Okay, we're supposed to find the internal loading and for reference, E is just to the right of the 3 kip load. It is not directly under the 3 kip load, it is just to the right of it. Okay, so the 3 kip load is applied infinitesimally to the left. Okay, so what do we do? What's the first step? Yawning, apparently, is the first step.
I take the, is that a distributed force up there?
Yeah.
I take the integral of distributed force and find the centroid of that shape of the distributed force and turn it into a.
That was my first choice, but that's an allowable first choice. So you have 1.5 kip per foot. What is the resultant force going to be? One-half kip per foot, distributed over 1.5 kip per foot up here. That's the peak value, 1.5 kip per foot. The peak value distributed load. What's the total? How do I find the area of the curve?
The area under the curve
In
integrate. We already know what it is because it's a triangle. So can we just multiply 1.5 by the area of the triangle, which is 1/2.
Right, it's 1/2 base times height. The area of the triangle is 1/2 base times height. Right, the integral is 1/2 base times height.
So it's 1.5 times 12 times 1/2.
Right.
18 kips.
So it's 9 kips.
9 kips.
Right, it's 1/2.
That's half.
So 9 kips
Okay.
applied at what position?
That was rough.
Where is that 9 kips applied?
2/3 of 12.
Relative to point D.
2 feet to the right.
2 feet to the right of point D. Right, 2/3 of 12, which is 8, so 2 feet to the right of D. Okay, all right. So now we've done that. What next?
Figure out what we want to find.
We can do some of the moments about B.
Okay, we're jumping a little too far ahead of ourselves. Do we have all the forces? No. Do not have all the forces.
Support reaction.
Right, so I've got to draw, I've got a reaction force here. And I've got, depending on how I want to do it, if I want to treat the whole thing or internally. But at the very least, I probably have reaction forces here and here, or whichever way you want to draw that. I'm not, one thing you'll note in here, I'm not anal retentive about the drawings. Okay, you have to have the drawings, they have to be clear and legible. I don't expect a straight edge, I don't expect, you know what I'm saying? So, I just need to, and I'm not, there are a few things where convention matters, other things where it doesn't, as long as you're self-consistent. Okay. And there could be a moment out here too, I guess. Okay. So we don't know any of those things. And we certainly don't know what kind of, we already said this is a pin, right? So there are potentially 2 reactions there as well, depending on which way to look at it. Right, we got all kinds of external forces to mention. In external. So, my suggestion would be a free body diagram. Okay. That would be normally my first step. Okay. Turning this into 9 kips is a valid point because you don't need to do, that doesn't matter whether you've done the free body diagram or not. But then once you've got that, you need to have a free body diagram. So, free body diagram, I'm going to do the member on the left first, because I want to find point D. Then I'll go back and do the member on the right. All right. So the member on the left has a force at A. Call it B sub x, B sub y. Actually, just call this A sub y because there's no A sub x. And then I've got my 9 kips here. That's all the forces on the left side. right? Now, what do I not know? Bx, by, and ay. Don't know any of them. What am I gonna do?
Sum equals zero, so if, like, sum of your modes and forces equals zero.
All right, so what do you want to do first?
Well, Bx is the only one in the x direction, so you can sum the forces in the x direction.
Okay, so we look at it, and by observation, identify that Bx is equal to 0. Right, by inspection. If you say by inspection, you better really, it better be, that's okay, but you better make sure that it's legit. You don't look at the picture and say, oh, well, by inspection, D equals 6.24 kips. Okay, what else? What can I do next? Somebody said something about sum of moments. Moments about what point?
Y or B, whichever one you want.
A or B? Yeah, A or B.
I say Y or B.
So take the sum of the moments about B, let's say. That's equal to, let me go back in here, but this is 8 feet, this is 4 feet. So the sum of the moments about B, that's just 9 times 4 minus A times 12, that's equal to 0. So A is equal to 3 kips. Good? Place AY here with 3 kips. All right, what's BY?
6 kips.
6 kips. All right, sum of the forces in the Y tells me that BY is equal to 6 kips. All right, so I would expect you in that case not to say by inspection, but to say sum of the forces in the Y equals 0, therefore BY equals 6. Right. Okay, so now I have my reaction forces. I got to find the internal loading at D. How do I do internal loading? What method do I do to find the internal loading at D? Hmm? I would take a section. I would do a method of sections kind of approach. Right, so now we're going to cut it at D. Right, so this is A, and this point here is D. And then we got to look at the sum of the force and do the same thing on this member. Right? So I still have this. Right? This distributed load on that point. And I have my 3 kips. I have my 3 kip force pushing up here. What's this? I'm going to find my resultant force there.
You could do trigonometry with a triangle and do it that way.
Seems
I'm sure
cool.
there's a shorter way to do it.
Yeah, it's a shorter one.
The way you're looking
You know, we get this and say, well, that similar triangles, this is half the size of that other triangle, right? All the dimensions are half. So that means the height,
Is the area is not half though, right?
no, area is a quarter,
But
but
the
we'll
height,
get to that.
the height is half?
Right, so this is 0.75 at that point. You see? And the width is 6 instead of 12. It's 1/2 base times height. The base is half, the height is half, the whole thing is 1/4 what it was before. You follow that? Okay. So I have 2.25 kips pushing down there. Right? Make sure I didn't lie to you. Yeah. Okay. Mental math. Where is that located? Where is that being pushed? Where is that pushing down? How far from D?
Oh, how far from the D?
How far from D?
Times 3 times 6.
Or 1/3 times 6, yes.
Yeah, that, yeah.
2 feet. Right? And so now I can do all the work. What is the normal force at D?
0.75.
What's that?
0.75.
No, what's the normal force at D? This is N. The normal force at D. The internal loading is your normal force. What is it? 0. Right, so N equals 0. Sum of the forces in the x direction. There's no normal force. What is the shear force at D? 0.75, up or down? It's one of those two.
It's down.
0.75 in this direction. And how do I find the moment? This one's the one we have to calculate. Sum of the moments about D is equal to 2.25 times 2 minus 3 times 6. Right? Right? So that's 4.5, so that's 18 minus 4.5, 13.5 kips. So is my sign correct based on the way I've drawn everything? So the bending moment.
Wait, it's like chip feet.
What's that?
Maybe those chip feet.
Kip feet, yes, units, kip feet, you're
Is
right.
that the right unit?
Kip feet, yes?
Okay. I don't know if chip feet turned into something.
No, kip feet. But is the sign correct? Is that the correct sign? Have I drawn, based on my drawing, is that the correct? Should it be positive or negative?
It's gonna be the main.
All right, I'm gonna make everybody vote. Positive or negative?
Sorry, I have to go. I get to practice in 6 months.
All right, that's all
Sorry.
right. What's your vote, positive or negative?
Positive.
All right. Positive or negative, come on. All in favor of positive?
Positive.
I have
I'm going against the grain.
All in favor of negative?
You voted for
We're
both.
voting for both, man. Put your hand in, you vote for both. It's positive. So this thing's trying to bend it in that direction,
Yeah.
right? Because this is pushing in that direction.
Positive moments counterclockwise, right?
So-
If your thumb's pointing around the board, it's.
Right, that's positive. Right, so this has to be, but the point is, I've drawn it this direction. The question is that the correct direction? Do I want to twist it this way? And I have to, because this is trying to twist it that way. Right, this is the larger piece. Right, the 3 times 6 is the larger piece. It's trying to twist it that way. So I need to apply a twist in this direction. All right, so there you have it.
First day.
You know, jump in with both feet, baby.
Yeah.
It's better than my first 2 days of camp.
First 2 days of Ken.
Yeah. The first day, he was like, so if you're in here, it means you'll probably be taking more chemistry. And then Ben and I rolled our eyes at that. And then he
In
talked about
chemistry right
his
now?
children. Yeah. And then he talked about his children for most of the class. And today, he finally went over the syllabus.
He didn't even go over the syllabus in the first day class?
No, because he's like, normally after the first day of class, it moves around by about a dozen people, so I'll go over the syllabus tomorrow.
Keep in mind, it's all recorded, so, you know.
What?
It's all recorded, so don't say anything bad about it.
Daddy, don't get hurt. I'll see you Friday morning.